SBO is the best.
Let's lock in. This is one of those topics where you can't just wing it because you need to truly understand it so you can answer a huge range of exam questions that link to performance, training, tactics, and recovery. In this video, we're going to look at what energy is, how ATP is made, which energy pathways dominate during which type of exercise, why fatigue happens, and how recovery actually works. So by the end of this video, you should be able to look at any activity, whether it's a 100-meter sprint, 400-meter sprint, javelin throw, football, boxing, marathon running, and be able to explain which energy systems are working and why, what causes fatigue in that specific context, and what recovery processes matter the most immediately versus over the next 2 hours versus over the next 48 hours. And lastly, be able to talk about the effects of warming up and priming before a performance or physical activity. So, what is energy? In PE, energy is basically the capacity to do work. And work is when you apply a force to move something, to move an object through a certain distance. So, for example, when you push the ground during a sprint, or when you're lifting a barbell, or when you're throwing a shot put, and force is how fast you do that work. Your body is constantly converting from one energy source to another form of energy. So these are different types of forms of energy that you need to know. We have mechanical energy, electrical energy, potential energy, kinetic energy, and chemical energy. In the body, energy ultimately comes from this molecule called ATP. ATP stands for adenosine triphosphate. So it's a molecule which gets broken down to release energy. So to release energy, ATP must be broken down. And this process of breaking ATP down to release energy is called hydrolysis. But because you actually don't store that much ATP readily available in the muscles, ATP has to be constantly replenished to provide that immediate source of energy. Because ATP is so great because it provides energy immediately on the spot. But because you don't store a lot of it in the muscle, you have to actually replenish it. And we call this resynthesis. So ATP resynthesis has to constantly occur to provide energy. And there are three sources of fuel that you need to know that help with this resynthesis process. And they are phosphocreatine, which is also known sometimes as phosphagen or creatine phosphate. We also have glycogen, which is stored in the carbs and the carbohydrate that you eat, and is mainly stored in the muscle and liver. We also have fat, which is a very large energy store and is mainly stored in something we call triglycerides. So where is it stored? Triglycerides. And remember that phosphocreatine is mostly used where there is a short duration and a very explosive activity. Glycogen is mostly used in flexible context where the activity is both anaerobic and aerobic, and fats are usually used as a source in an activity that is high duration, relatively slow, but requires a huge capacity to last a long time. So like marathon running. And even though these three sources of energy are beneficial for different types of exercises, like we spoke about, for example, PC might be most beneficial for something like a 100-meter run, glycogen for something like an 800-meter run, fat for something like a marathon run, they all intermingle when we talk about the three energy pathways. So we're going to talk about ATP-PC system, the glycolytic system, the aerobic system, and these energy pathways rely on different sources of fuel to replenish ATP synthesis. But these energy pathways, it's important to know that they don't work alone, right? All of them contribute in certain ways all the time. What you want to be focusing on is which one is dominant based on the intensity and the duration of exercise. So we're going to start looking at the ATP-PC system before we move on to the glycolytic system and the aerobic system. So the ATP-PC system, or also known as the phosphagen system, is an energy system or energy pathway that is designed for maximum intensity and very short duration work. So think of a sprint start, a jump takeoff, a javelin throw, a lift, a powerful lift in a powerlifting competition, or a powerful tackle, things like that. So what happens in the ATP-PC system? You use the stored ATP in the muscles, which releases energy instantly, and it releases energy that lasts for a few seconds. And when ATP drops, you need to replenish, you need to resynthesize more ATP to continue using energy, right? Because you don't want to be fatigued. So when that ATP drops, to replenish it, you have this PC molecule. Remember, what does PC stand for? Phosphocreatine. You have this phosphocreatine molecule that donates a phosphate molecule. So I'm going to denote a phosphate molecule with a P. It donates a phosphate molecule to ADP. And where does ADP come from, you may ask? Well, ADP is sort of a byproduct of when ATP breaks down. So when ATP breaks down, it gets broken down into something called ADP, and it also gets broken down into something we call an inorganic phosphate. But just know it gets broken down into ADP. But this ADP, for it to become whole again and for it to become an ATP again, it needs this P molecule. So, very thankfully, we have a phosphocreatine that is willing to give a P molecule to the ADP. And the ADP says, thank you very much, PC. It takes that P molecule and it adds it to be able to rebuild an ATP molecule. And then the whole process repeats again, where the ATP breaks down, releases energy, then the ADP gets replenished, and then it goes back to ATP, and then it breaks down, releases more energy. So that's how the ATP-PC system works in a nutshell. And the key characteristics of the ATP-PC system is that it has the fastest speed of ATP production, it produces the highest force or power output, it has very limited capacity, so it only lasts a few seconds. We're going to look at the exact amount of time it actually lasts for, when it peaks and when it completely gets depleted. And lastly, it has minimal acid or harmful byproducts as compared with other processes that are used to generate energy, like something we're going to see called glycolysis. And that's why it's referred to as alactic sometimes, which means without producing lactic acid. Okay, let's move on to the glycolytic system, which mainly works through a process called glycolysis. So once you've used up the ATP from the ATP-PC system and the ATP-PC system sort of gets exhausted, your body then moves on to the glycolytic system and it uses glycolysis to synthesize ATP by breaking down glucose or glycogen to resynthesize the ATP without needing oxygen. So this is still quite anaerobic. This process called glycolysis is still quite anaerobic. And how exactly does glycolysis work to be able to resynthesize ATP? Well, it's a very long process, but basically what you need to know is that glucose and glycogen are broken down to be able to resynthesize ATP very quickly without needing a constant supply of oxygen. Because think about it, Sometimes you might wake up and just start running and you need energy right there and right then. But the thing about oxygen is it actually takes quite a bit of time, a few minutes, for oxygen to properly be used to release energy in the body. But your body doesn't have a few minutes. If you want to run, you need energy right there and then to be able to run. So your body goes to the ATP-PC system, but the ATP-PC system only lasts for a few seconds and then it doesn't work anymore. So it has to use the glycolytic system. And the glycolytic system, because there isn't a supply of oxygen that actually matches the demand of energy that your body needs, it needs to find another way that doesn't need oxygen. And so that's where glucose and glycogen is used to be able to release energy from ATP. And the characteristics of the glycolytic system is that it produces ATP faster than the aerobic system, but slower than the ATP-PC system. It has greater endurance than the ATP-PC system, but not as much endurance and capacity as the aerobic system, and it produces a byproduct called lactate or lactic acid, which builds up in the muscle and which can interfere with muscle function and make the muscles less efficient. Okay, now let's move on to the aerobic system. The aerobic system mostly happens in the mitochondria. So the aerobic system produces ATP the slowest, but it produces the most ATP. So it has the highest yield of ATP. It also has the highest capacity or endurance, which means it can last for the longest time. And the byproducts are carbon dioxide, CO2, and water, H2O. But how does the aerobic system actually work? So this one is a little bit more complex than ATP and glycolysis because it doesn't just rely on one process to resynthesize ATP. It relies on up to 3 processes. So the aerobic system starts with glycolysis, which is the first stage. And then, as more oxygen is available, it moves into the mitochondria processes, which are the Krebs cycle and the electron transport chain. The electron transport chain can sometimes be referred to as something we call oxidative phosphorylation. Oxidative phosphorylation. And the aerobic system, like we mentioned, produces the most ATP aerobically. So it produces a little bit of ATP with glycolysis, but it produces the most with these other 2 additional processes, which again are very lengthy processes involving loads and loads of enzymes. Now let's talk about comparing the energy pathways. This is where you can pick up a lot of marks. So if you get a question asking you to compare pathways, you always want to be referring to these type of things. So you want to talk about the ease and the speed of energy or of ATP production. So obviously the ATP-PC system has the fastest speed, glycolytic has a fast speed, and aerobic has the slowest speed and ease of ATP production. We're going to be talking about the force of contraction. So ATP-PC supports the highest force or power output. Glycolytic supports high power, but it drops over time. And aerobic system supports low power, but it sustains it over time. We're going to be talking about the intensity and duration. ATP-PC system is very explosive, but has low duration for the activities that it supports. Glycolytic system has high intensity but sustains the high intensity for a little bit longer, and the aerobic system supports high duration and low intensity exercise or activity, but for a longer and steady time period. And you want to talk about ATP resynthesis, so how ATP is regenerated, and in the ATP-PC system is regenerated from that phosphocreatine molecule, so that PC donates one of its phosphate molecule to be able to resynthesize ATP. Glycolysis uses glucose and glycogen, and the aerobic system uses respiration, which uses oxygen and fats as well, and glucose as well, because remember, the aerobic system also uses glycolysis. Now let's talk about something known as the energy continuum. So the energy continuum is a way to map events based on where each energy pathway is most predominant. So we can see on this graph, let me break it down what exactly this graph is telling you. So this graph shows the interplay of different energy systems over time. And each line has a different color. So I'm just going to change my color right here. So this green line represents the ATP-PC system. The black line represents the glycolytic system. And the red line represents none other than the aerobic system. So basically what this is showing is it's showing the amount of time that each of these systems are really dominant and are really working the hardest before the next system takes over. And for the ATP-PC system, it works for about 10 seconds before we see the glycolytic system start to take over. So it's really efficient, really effective up until 10 seconds before it starts to die down. Then the glycolytic system takes over, and it's really effective up until 3 minutes before the aerobic system takes over from 3 minutes, and it can carry on for minutes and hours long. Again, it's very important to be able to know which sorts of real life activities fall under these three energy systems. So again, something like a 100-meter sprint would be very ATP-PC dominant because it's very explosive, it's very short, and it's around that 10-second mark. Something as well like a 200-meter sprint will still be very ATP-PC dominant because it's still predominantly powered by that ATP-PC system with just a little bit of the glycolytic system acting towards the tail end. A 400-meter sprint would be heavily powered by the glycolytic system because it's going to last for longer than that 10 seconds but less than 3 minutes. 800-meter run, can't really call that a sprint anymore, would be sort of in the middle ground. So it would be a mix of the glycolytic system and the aerobic system, and something like a 1,500-meter run and anything above would be aerobic system dominant. Okay, so these energy systems, they all produce energy, but one thing that happens to all of them is fatigue. So when you work, over time you get tired, you get fatigued. And what is fatigue? Fatigue is simply the point where the body can't maintain the required amount of effort, force, or power or pace anymore. So your output drops, your technique breaks down, your decision making gets worse, and your performance can fall off. The three main contributors to fatigue are energy depletion. So this is just when the source of energy gets depleted. So whether it's phosphocreatine or glycogen or fats get depleted, so you can't maintain the intensity of exercise. 2, we have dehydration. So dehydration reduces performance because it disrupts the fluid balance in the body and can reduce effective circulation and thermal regulation. So when you sweat, you lose water and electrolytes, and this makes it harder to sustain output and to cool the body effectively, which is what thermal regulation is. The thermal regulation, which is spelled like this, thermal regulation is just the process of keeping the body temperature at a good temperature so that you don't get too hot or too cold. Next, we have waste products and lactic acid. So in high intensity work, the pH level, which is the level of acidity in your muscles, gets lower. That causes the acidity in your muscles to increase. And that acidity increase, coupled with the production of the lactic acid byproduct, causes a drop in the muscle function. And that's why you get a burning sensation in your muscles when you're working highly intensively. And because exercise or physical activity or performance can be so draining and it can cause a lot of fatigue, we need a way to be able to recover and replenish the body after the performance. And that's where recovery comes in. So we're going to look at something called epoch, and we're going to look at the fast and the slow components of epoch. So recovery basically links to epoch, and epoch means the extra oxygen that your body consumes after exercise above resting levels to be able to return to its normal function. And this consists of two stages or two components. We have the fast component and the slow component. So the first component of epoch is the immediate recovery phase. So this is what happens in the few minutes of stopping exercise. So you finish exercise, you finish a performance, and those few minutes where you might still be tired, you're still panting, you're like, this is what happens. So what happens is ATP-PC gets resynthesized. This process is called rephosphorylation. So rephosphorylation is the process where ATP-PC gets resynthesized immediately after physical activity, rephosphorylation. Next, what happens is the reoxygenation of oxygen stores in the blood and the muscle. So hemoglobin and myoglobin gets resaturated with oxygen. Hemoglobin is that protein we spoke about in a previous video that helps to transport oxygen in the blood. Myoglobin is something found in the muscles where oxygen is stored. And lastly, what happens in the fast component is there is a rapid drop in the ventilation and the heart rates. Then we have the slow component. So this is where everything takes a bit longer. It might take minutes, hours, or even days, depending on how intense the physical activity was. So what happens in the slow component of recovery? You have oxidation of lactate and the removal of lactate. This is interesting because lactate, yes, it's a waste product, but it can actually be turned back into a useful product that can be used to release energy. And that's when it's oxidized. So oxidation is when you add oxygen to the lactate and then that turns it back into a source of energy again. Or you can just remove the lactate entirely. Next, we have replenish energy stores. And next, this is what happens in a 2-hour window. We have elevated body temperature. We also have physical cooling of the body. And next, in the 48-hour window of opportunity, we have synthesis of protein and glycogen. And also in that 48-hour window after exercise, we have the repairing of damage. So damage such as exercise-induced muscle damage and the damage caused by delayed onset muscle soreness. So when you hear of DOMS, that's delayed onset muscle soreness. And when you hear of EIMD, that's exercise-induced muscle damage. Lastly, let's talk about how energy systems respond acutely to the stress of warming up or priming. Remember, when we talk about acutely, we mean in the short term, we mean immediately. So a good warm up or priming, what it does is it increases muscle temperature and enzyme activity, and this makes energy production run more efficiently. It also improves oxygen delivery, it speeds up oxygen uptake so that the aerobic system can be able to be more effective. And lastly, it reduces the initial oxygen deficit and delays heavy reliance on anaerobic glycolysis at the start of performance. So oxygen deficit is a term which basically refers to what I was talking about earlier in this video, where I said sometimes when you start exercising straight away, the body can't provide enough oxygen to be able to meet the energy demand. So your body has to produce energy or release energy anaerobically until the oxygen that your body is able to provide to your muscles can actually catch up with the demand for energy. So until then, your body is gonna work anaerobically, and in that time, it's building up an oxygen deficit. That amount of oxygen that can't be used quickly enough is the oxygen deficit. Okay, that's it for this video. This is one of those units where you just can't wing it. You have to practice. So I highly encourage you to check out superpeonline.com for our practice resources on there to really help you get those top marks. All right, see you in the next video.